Okay, I'm going to start. Since the majority is sitting here now, I'll probably try to move mostly to this board. And I put the owl here. Hopefully, people online can see you as well as the board. I'll try to also walk that way. It's always a strange room to me to manage the split brain audience. But okay, do our best. Welcome everyone. Happy to see you all in such a great numbers. And I understand that there's even more people online. At the moment, we are at 49 people online. I'm not going to count, but almost 50, I'd say. So, first course on machine learning for chemists. That's the plan. And do I get rid of this little thingy here?
Bernd, can you switch the microphone? They say the quality of the sound is not great. Maybe you have to use the microphone from
this one.
The setting in the Zoom. From using the microphone from your computer.
Instead of the owl, you mean? Okay, let me see if that's possible. So now I'm using the owl, and you're telling me to use my laptop one. Do you think this is better? Okay. See what people say online.
Much better.
Much better. Okay. Well, sorry, I'll hide video panel. Hide. Okay, good. Yeah, this will be good. Okay, so here's the plan. It's 3 parts. I'll start with half an hour to 40 minutes of introduction on machine learning. Then my partner, Robert Pollice, that you may have already seen this morning at the seminar, assistant professor in Groningen, will take over and show some very cool applications and go through them step by step. And especially that part is going to be very interactive, I understood. So feel free to ask the questions. And then finally, we're ending with a little quiz, with a little exam. So please take notes, be prepared, because you will only be able to download, well, not able, allowed to be download the certificate of participation if you scored at least a 6 out of 10 to the online exam. Okay, so we're very, very tough. You're only allowed to put this on your CV if you do well. So better pay attention. So the plan is we actually have some learning objectives, and I'm going to try to explain the overall workflow of machine learning. So that's one of the objectives. So how do you deal with data? How do you choose the model? I'll discuss 2 possible models, machine learning models that I use a lot. One of them being neural networks. Then how do you train them and how do you validate them? And then the inference part is done by Robert. How do you apply these machine learning models? Of course, another learning objective is I'm going to throw as much jargon at you as possible and try to explain everything so that you can walk your way into some into the machine learning collective, right? So that's another plan, and yeah, prepare you to work with your colleagues and students that are working on machine learning. So they need to know what they're talking about and interact with collaborators. And of course, the fourth thing is to become a certified for the master. But yeah, as I said, you have to be passed this exam. And then the last one is actually for Robert and me. This is the first time that we're doing this, that we do such a crash course and try in 2 hours to make you all experts in machine learning and chemistry. So it's very ambitious. So we hope to learn a lot as well from this experience, and we'll follow up with a little questionnaire to find out if this was actually useful, if you recommend it to your colleagues, and if you would actually be interested in a follow-up and should we do this more often? Okay. What is machine learning? I start with a very brief history. This is actually generated by ChatGPT. I asked ChatGPT to give me a very brief history. So if you want a longer one, just go to ChatGPT now for a longer history on machine learning. But machine learning and AI may actually be older than you think, right? So, I mean, these ideas are at least 100 years old, I think. People talking about cybernetics, robotics, machines that can learn, etc. But the term artificial intelligence is actually from a famous Dartmouth workshop from 1956. So quite old. And people were thinking about, well, symbolic reasoning, for example. And then actually got a bit of a setback, so-called AI winter, and funding dried up after people got disappointed in what they actually could do. They thought it had great promise. Oh, okay. I'm not allowed to move. I try to. You move away. Ah, okay. Yeah, and then yeah, so okay, I'm not going to go through all the steps, but maybe one important step is the 1986 backpropagation algorithm. It's very, very useful because it allowed it to actually optimize large neural networks, and I think that was one of the things that great Geoffrey Hinton got a Nobel Prize for developing these things. He's there again in 2006. Deep learning research as a powerful technique with Geoffrey Hinton, breakthroughs in training and deep neural networks. Before, in 1997, maybe you remember some of what they do, IBM's Deep Blue defeated chess champion Garry Kasparov. And it showcased AI potential in strategic reasoning. Mind you, that was not machine learning. That was just the code that was following rules, but it didn't get better by playing more games, okay? It was just all hard-coded. If this is a situation, then do this, etc. This still counts as AI, but it's not machine learning. Later on, in 2016, Google DeepMind's AlphaGo defeats Go champion Lee Sedol, which no one expected because Go is much more complicated to calculate through than chess, actually. So that was really impressive. But that was actually real machine learning, right? That would actually learn. In fact, the way they trained this was take two computers with a machine learning program, have them play against each other. They would play 1 million games per hour. And in one day, they were stronger than the best human player. Then you see, the density of events gets quite high in the last part. 2017, transformer models revolutionized natural language processing. 2020, GPT-3, only 4 years ago. Now we are all using GPT-4 or something like this, I imagine. AlphaFold, 3 years ago, another Nobel Prize there. And currently we're in the age of generative AI. And when I say age, I probably mean 5 years or so. Things go so fast. Okay. Now, so people always talk about AI or machine learning or deep learning. What's the difference? Well, there is a bit of a hierarchical difference because AI is more than machine learning. It is also computer vision, natural language processing, robotics, etc. In general, it is AI, artificial intelligence, systems that simulate human intelligence. Okay? And only machine learning counts as algorithms that actually learn and they improve from data, right? So you should have a measure, a performance measure, like a loss or an error function that should get better the more data you put in, right? So if some task, you can measure how well does it do the task, and the more data you put in, the better it gets. If that's the case, we're talking about machine learning. It's a machine learning algorithm. There's different sorts of machine learning. I'll talk about that in the next slide. And then finally, what is then deep learning? Well, deep learning is just, again, a sub-branch of machine learning. It refers to neural networks, and in particular, rather big neural networks. And so large neural networks such as large language models, for example. Okay, and today I will only talk about machine learning, and yeah, and then there's different kinds of machine learning. So time to pay attention because this will now come back at the exam. Yeah, I'll distinguish three types of machine learning: supervised learning, unsupervised learning, and reinforcement learning. Then there's also examples around that, but that's too small for you to read. Don't worry. I'll tell you first what is the difference between supervised and unsupervised learning. Supervised learning is I have data that I want to learn from, and for all the data points X, I also have an example, it targets Y. So I can learn from examples, right? So this is called so-called labeled data. Each data point has the label of what I want to learn. For example, regression, for each X value, I also have the Y value, right? And so I can try to learn a fit to my data points, or classification. For example, I want to recognize cats on pictures, and I have tons of pictures of all sorts of animals, and they are annotated. It says, you know, this is the cat, this is the dog. And so I can learn again from examples, and I can check if my machine learning did a good job or a bad job, because I have the target, I have the labels, I know the answers. The only difference between regression and classification is regression deals with continuous numbers, and classification is discrete numbers or pictures. Or you already have a question?
Yeah. Well, one question is,
yeah.
Can the people online take the exam?
Yes. If you have a telephone, you can do the exam because it will be online, multiple choice. And I won't check if you're collaborating and working together on WhatsApp.
And the other is just a reminder to speak towards them.
Yeah, I'm sorry. I do my best, but yeah, no, it's hard to point. But okay. You know what? I'll point with the. Is this visible? Well, okay. So then supervised learning is also, I already have a ton of data that I can learn from, but I don't have examples. So I don't know what should come out, and what can I do with that sort of data? Well, again, two classes. I can cluster the data and maybe based on similarity, find patterns. For example, similar molecules, right? In the context of chemistry, I can try to cluster them together. Or if I'm analyzing photographs of X-ray from lungs, I could try to classify in different types of pathologies, for example, right? And the other one is a dimensional reduction. Maybe, I think some of us have probably used PCA, principal component analysis. Maybe it's a way to reduce the dimension of the amount of variables. I see Fred doing like this.
Do we call that learning?
Yeah. Yes. Yeah. Especially if you have high dimensional data and you have to, you cannot just stare at it. You need an algorithm to actually learn. And of course, PCA is older than machine learning, I would say, at least since the last revolution of machine learning. Although you just saw machine learning is actually quite old. But nowadays, yeah, you'll see PCA as a type of machine learning. Now, PCA is then the simplest form because it's a linear representation, and nowadays it's much more fancy ones. But yeah, PCA is the first out of a class of dimensional reduction methods. And then finally, what is reinforcement learning? Well, that is when you have no data at all and you're going to learn on the fly. And for example, these games that I talked about, like learning Go or chess, yeah, was just done by doing tons of games and then learning how to improve from the results. And each game you play is another data point. It's basically how humans learn how to walk, right? You try and you fall, and then you learn what not to do and what to do instead. I also added here Bayesian optimization, which is not a type of reinforcement learning, but we'll hear about it later as an example from Robert. And that's something that is used, for example, to automate or robotize chemical experiments, for example, right, with Bayesian optimization. So you try to maybe improve the yield by playing with the parameters, and the method to do that is Bayesian optimization. Although in principle, you could also use reinforcement learning, but you'll hear more about it. The thing to remember now is that we have these three classes, and depending on whether you have labeled data or non-labeled data or no data at all, you'll be doing supervised, unsupervised, or reinforcement learning. Okay, I would like to, well, one thing that I would like well, that you all know at the end of this first lecture is the overall machine learning workflow. That is, what you always need to do, which is a bunch of steps. First of all, you have to deal with training data. You have to find data, and often you have to do something with the data before you can use it. Then you have to choose a model, a machine learning model. You could use a neural network, but there's actually many different machine learning models. And you have to train the model. That involves also a bit of steps and delicacy. And then finally, we'll do the inference. And so we'll always do it. And I will go through these things step by step in the rest of the lecture. Of course, we first have to decide what we're going to do. So actually, there's also step 0. We should first define what do we want to do? What is the task, actually? But then once you've decided the task, are we going to do clustering? Are we going to do some regression, etc.? Then the machine learning workflow is always, how do we get data? How do we get the right information out of the data? Choose the model, train the model, and finally use the model to do predictions. About which machine learning task, well, I already told you we have supervised learning, unsupervised learning, and reinforcement learning, so that should be decided at task 0. And maybe another thing that I want to stress is the so-called first rule of machine learning. Don't start with machine learning if you don't have to. Machine learning is complicated and maybe expensive. If there is a good heuristic, maybe that's better. And it's in any case a good thing to start with. Also because it will always give you a nice baseline to compare machine learning against, right? Because, well, machine learning, well, there are some difficulties sometimes, and yeah, you want to compare it to some baseline to see if you actually learn anything. And so it's a scientific approach is to first start with a baseline method before you actually do jump into machine learning. Rule number 1. Okay, so we have decided on the task. Let's take as a task. We're going to predict the solubility in water, and we have some data. Let's say we have 1,000 data points, which is a list of molecules and their solubility in moles per liter. So I hope you agree that this, is then supervised learning, because I have actually examples, answers. I have the solubilities, the labels of these data points, these 1,000 molecules, right? So that means supervised learning, and it's continuous data, so it's a regression and not classification. Okay, let's have a look at now this training data. What should we do with it? And in particular, I'll tell you a little bit about feature extraction and exploratory data analysis, and I want to teach you a little bit about molecular representations. So, yeah, it's very important that before you start using data, you have a look at your data. And this is called exploratory data analysis, or EDA in short. So you should always first examine your training data sets, and maybe compute some statistics, calculate the mean, calculate the variance, maybe plot some distributions. Is it a Gaussian distribution, or is it a heavy-tailed distribution? Or maybe there's no spread at some features at all, in which case you could ask, is this really useful data, etc. If you have high-dimensional data, so maybe you measured many things that you want to, right? Maybe you measured, yield and temperature and pressure of something that you want to use as input to now predict something, or maybe cluster molecules, or predict solubility or whatever. Then it's good to know in advance if maybe some of these things are actually correlated, because then adding an extra dimension, extra input feature may not be so useful if it's very correlated to some of the other ones. Often there are outliers. So check if you don't have anything weird in your data. And often, yeah, also even if you download cured data sets from the web, it may have weird, infinites or maybe some rows in your sheet are missing, etc. And so you probably need to clean up your data a little bit. So always first have a look at your data, because otherwise you may discover your machine learning method is doing weird stuff and it's just your data. And well, the rule is what is the rule? Crop in, crop out, or something like this. I forgot what is that. I think there was a more friendly way to say it. But anyways. Sorry?
Garbage in,
garbage in, garbage out. Thank you. That's better than crop here. Then what about feature extraction? Very often you cannot use directly the raw data, but you may want to transform the data into something that helps your machine learning algorithm a little bit. Right, so you may want to pre-compute certain features. For example, suppose that you have coordinates of molecules, but the molecules are not translated with respect to some zero of some coordinate system. Then yeah, translate them maybe. Right, so if you have pictures of cats that you want to learn from, it's a good idea to make sure that the cats have all the right lighting. The cats are nicely in the middle of the picture with the same size, more or less. That usually helps the machine learning algorithm a lot. So you may want to scale or normalize the input. You may want to use molecular descriptors for chemical problems, and I'll teach you about 3 molecular descriptors in the next slide. And sometimes you can actually also use another model to learn good features and select what are good features. Right, but it may be obvious that the choice of the input features is very task dependent, and so that's hopefully also typically something that you learn from the EDA. What are actually the good features, and maybe you have to massage them a little bit to get good features to learn from. But if you have done that, then yeah, you can start thinking about the second step. Now, what about molecular representations? If you want to learn to predict solubility, what is the task at hand of a bunch of molecules, how should your machine learning know about these molecules? Can you just give the names? Ethanol, alcohol, propane, the names, or should you use something else, like pictures or something like this? Well, there's 3. One is graphs. So you can actually make a graph of your molecule. So there's the 2D structure of a molecule, and you can make a graph out of it, where you just take the nodes as the atoms, and the connecting lines, the so-called edges, are the covalent bonds. Right. So and then in those graphs, typically, vectors or matrices are connected to all these nodes and edges that contain information that can be used for the machine learning. For example, maybe the nodes vectors contain information about well, the element name, but maybe also the positions or the charge or the mass. Maybe the edges tell you something about the type of bond. So the bond order, is it covalent or is it another type of bond, etc. And this sort of graphs are used a lot in something called graph neural networks, which are special operations that then work on those graphs to get features. So in that case, you actually generate features. They are machine learned features, so difficult to interpret maybe, but very useful for the computer. That are then used in a neural network to predict something like solubility, for example. Unfortunately, I cannot explain in this short crash course what graph neural networks are, so that will be a more advanced course, I suppose. But you may come across that term. It's a hot topic at the moment. And are you going to say anything about graph neural networks? No. Okay, so that would be a follow-up. But so graphs are an interesting representation of molecules. Another one are strings. Right, you can represent molecules as strings, and there's different, let's say, languages that you can use. The most famous one is SMILE, You may have heard about smiles, because if you look up a molecule in Wikipedia, there will be a list of properties, like what's the melting point and the structure, etc. But you will also find the smiles code typically.
There is a question from the chat, which is, how do we know the geometry from the graph?
You do not, and you don't need it. So the graph doesn't represent geometry. It could be encoded. All you know is what are the connections, but what is the 3D structure is not encoded in the graph per se. Yeah, there's all sorts of languages. Other than smiles, there's something called selfies, smarts, deep smiles, etc. But smiles is the most known one. And there's two examples there. CC means ethane. So hydrogens are usually implicit. So yeah, right. So you only look at non-hydrogen atoms in these strings. The second one is acetic acid, which is represented as CC, and then between parentheses equal O. That means there's a side group with an oxygen with a double bond, and then at the end another oxygen connected to that second C. So the nice thing is that with a bit of practice, these smile strings are actually human readable, and you can find them in most databases. It's very often used. And using simple tools that you can find in Python libraries, other libraries, such as RDKit, they can easily be converted to other representations. So if you download a data set, there will often be a column with all the smiles of all the molecules there. And it's very easy to convert them, for example, to graphs or to, well, fingerprints, which is what I'll show you next. The syntax can be learned by language models, actually. It's really a grammar and the syntax, like English or Dutch, but then, yeah, chemistry. And you can use that to then to generate new smile strings and create new molecules, for example. And tomorrow we'll have a speaker visiting HIMSS, Francesca Grisoni, and she's actually using that to create new drug molecules from smile strings. There are some disadvantages, so they're not perfect. For example, they're not unique. So a molecule can be represented by different smiles depending on which end of the molecule do you start with writing C's and O's and etc. So CCO or OCC is both ethanol, and even this C with an O side group and another C means ethanol. So there's not a one-to-one mapping. There can be syntax errors. So if you produce smile strings, it doesn't mean it's a legit molecule. For example, this one is missing a closing parenthesis. And there can be semantic errors. For example, here we have an oxygen that's connected to a carbon, but then there's a double bond to another carbon, and that's, of course, not a stable molecule. And then the third representation is fingerprints. And fingerprints are just binary vectors with zeros and ones. Another question?
Yes. Do smiles account for stereochemistry?
Yes, I'll show you an example in a second. Because I will teach you the language of smiles, actually. That's another objective. I should have told you about it. I hope you're good in languages. So they're long strings, actually very long. I mean, sometimes 1024 zeros and ones. And they can encode all sorts of stuff. So obviously, they're not human readable anymore, because if you just look at that and I ask you which molecule is that, then yeah, no way. But yeah, computers, of course, are very happy with zeros and ones. And depending, where, so each position has a meaning. For example, it could mean things about the molecular structure, like does it have an COOH group, or is it aromatic? So it can have information about the molecule, the molecular structure. But it can also encode other stuff, like electronic properties, like electronegativity, dipole moments, or physicochemical properties, such as the solubility, etc. And so you can encode all sorts of stuff there, which can be very helpful to try to predict properties like solubility. So it's very good for property prediction. It's also very good for finding molecular similarity, but that's actually true for all of them, because you can very easily, compare two strings and see, okay, are the ones at the same positions and the zeros at the same positions? If yes, then well, they're probably very similar in property and in structure. But that's true for also, I mean, graph you can also easily compare, and even small things you can easily compare. Okay, here a little bit about language. I'm only going to the first half, but just to teach you how easy it is to read the smile strings. So there's just a string of atom names and some extra tokens. So the first two rows, well, except for the hydrogens of the periodic system, you just write the letters. More exotic elements are written in brackets. As I said, hydrogens are implicit. And if you see parentheses, it means the branch, right? So for example, CC, parenthesis C, parenthesis C. C is a dimethyl propane. There's two side groups. Here's a methyl group, here's a methyl group. And then CC, and the last C is propane. Single bonds are implicit, okay? So here we see no information about the bonds, so all the bonds are single. But if you see an equal sign, we'll have a double bond. And if we have a hash sign, it means a triple bond. And then, about rings. Rings are broken as just a string, written as just a broken string, with then integers added to the connecting atoms. So for example, OC1 and then CCCC1, it means that this last C1 is connected to this first C1, right? So it's a ring, forms a ring. So if you see a 1 and another 1, these two atoms belong together, they are connected. And maybe later there could be a 2 and a 2, okay, that's another ring, etc. So you can have as many rings as you want by connecting the ones that have an integer attached to them. This is about stereochemistry. Okay, I will skip this part, it's not so interesting, but you can see it's very easy to read these if you know these simple rules. There's more rules about stereochemistry, but let's skip that for now. Okay, that's about smiles formats and the different molecular representations. So now you know a little bit about how you can represent molecules in a computer and use that as input for machine learning, as data for machine learning. Any questions so far? Yes. Yes. Very good point. Okay, I see you already advanced. Because you're right. I told you that smiles strings are not unique. You can write different smile strings for a molecule. But then there are people that have tried to fix this with so-called canonical smiles. And then, there's rules about which side you start, etc. And then there's a one-to-one mapping. Unfortunately, there's different people that have tried to make canonical smiles. And so depending which program you use, there may be a different definition of canonical smiles. But yes, in principle, you're right. It's one-to-one. Yeah, you had another question?
Just a comment. Can you repeat the question?
Oh, yeah. So the question was, what about canonical smiles? Because those have a one-to-one mapping, and I just claimed that smiles have this issue with several smiles can represent the same molecule. Yes.
But I was wondering at what point is the data?
Oh, right. So at what point is, yes, data manipulation. So at what point is taking out outliers data manipulation? Well, that's completely up to the user, I would say. So you want to train a model. If you have some expert knowledge and you look at the data in which you measured something, and you see at some point very strange numbers, and you think, oh, clearly something went wrong in this measurement, I'll throw out the data, then that's up to your discretion, I would say. I don't know. There's no rules about it. Yeah. Yeah. Yes, exactly. So in the case of clustering, if there are some points very much outside, you could take them out or not. Again, there are no rules. So if you feel that those described data points that are not helping your machine learning and they are not going to give you the answers that you're looking for. Okay, this sounds already dangerous, very unscientific what I'm saying now, but I'm just saying it's up to you. There's no rules.
Will choosing different models vary the results?
Will different models, choosing a different model, change the results?
Yeah.
Yes, absolutely, yes. Yeah, and well, okay. And in fact, now I will talk about models, and I will also say a little bit more. In fact, I'm going to discuss two different models: decision trees and neural networks, which are two models that are used a lot, I think, in our community. Okay. So how about choosing the model? Well, it's very difficult to say something general about it because, first of all, there's a ton of models. There's a whole zoo out of there of different machine learning models. So it depends, of course, on the task. What do you want to do? Supervised learning, unsupervised learning, etc. But also about the problem. How complex is the problem? And so how complex a model do you need? Do you need a very large or smaller neural network, say, or maybe another tool, kernel methods, etc. Depends on how much data do you have, because if you don't have so much data, probably it's not a good idea to try to use a very large model with a ton of parameters. Leads to problems. I'll show you in a minute. Different models may easier or more difficult to train, right? So the model may not be so stable, difficult to converge, which, well, if you're not an expert, may lead you to choose another model. Some models create more transferable answers than others. Some models give you probabilistic outputs, which may be very nice, right? So it just don't give you just a prediction, but also, let's say, error bars, which is very nice. And some models are more interpretable than others. And I'm going to talk about two. Decision trees, which are very interpretable, right? They're like a white box. And neural networks, which are less interpretable. And you may have to do some effort to really understand where a prediction comes from. So first, decision trees. A decision tree, you can just try to think of as a flow chart with yes and no questions, for example, until you arrive at an answer. The thing that you use when you want to prepare for a political election and you want to decide, okay, on some issues, what is your opinion? And then at the end it tells you, okay, you should vote on this or that party. So some data goes in on the top. It's a tree upside down. So the root is on top and then the leaves, the green stuff is on the bottom, which are the different decisions that come out. And these things are called trees with branches, etc. And so, for example, maybe we want to use it for classification. And we have a lot of images with animals on it. And depending on each step, maybe the first decision node is, does the animal have pointing ears? If yes, then maybe it's very likely a calf. Or it doesn't have a very long neck, then, well, it's a giraffe, etc. Right? So so the aim of the game is, what are the good features to select on? That's what it has to learn. So we can use it for classification, but actually you can also use it for regression. And we have to learn the decision rules. What are the best decision rules from the input, from the input features? So the algorithm is as follows. You start at the root node with the entire data set, and you may have different features, right? So again, let's think of an Excel sheet with all sorts of columns of stuff that you measure, maybe, if you want to decide on solubility or, well, classifying different molecules, less or better soluble molecules, say. And then, so maybe, one column has a molecular weight and another one has a melting point, etc. And so what you will do is, you will try all of them. Well, the algorithm will try all of those features and figure out which one does the best separation in, group A and group B that is classifying. And you keep on doing that. So then you separate them, you find the best classifier, the best feature that separates into the groups that you want to separate it in. and then you add another decision tree node, and recursively you make new decision nodes. So you go back to 2 until everything is classified, and you write all in these. Well, they're called leaves, these terminal nodes. Okay. So yeah. Yeah, exactly. Yeah, you can use also combinations of features. That's true. Not. Yeah. Well, the fancy ones, yes. So yeah, you can take combinations, and if not, you can make combinations in advance. For example, if you use PCA, you find the principal components, which is a linear combination of the features that describes best the variance of your data set. And yeah, you can use those, which then automatically takes care of the most relevant combinations. Another question.
Is decision used in supervised learning?
This is supervised learning. Yes, you need examples. Otherwise, I cannot decide if I made a good criterion to change to separate in groups A and B. I need to know what are the groups, what are cats and what are dogs, say. So yes, supervised learning. Classification and regression is supervised learning. What is nice about decision trees? Well, they're very simple, they're very interpretable, because I can always just plot the thing after I'm done and see, okay, what is happening in the first, what's my first feature that I'm separating on, what's the second, etc. Or if I do now a new prediction, I can see, okay, how did it go through and why does it predict the thing it does? So it's very interpretable. It is a bit prone to overfitting. So if you have a very large network with many rules, then yeah, you may get problems of overfitting. I'll tell you in a second more about overfitting, but that means you have to do some pruning. So really, as with a tree in your garden, you would prune, take out leaves. You do the same thing here. Maybe you say, oh, leaves should have at least 10 or so of my data points. You cannot have just one data point in each leaf, right? So I should group things, or I can make the branches shorter or something like this. I can say, well, you have to decide within 5 steps, or you have to decide within 10 steps. You cannot have super long, too complex branches. And you can make more advanced versions of this one. For example, random forest, where you basically have many random decision trees next to each other in parallel. And you take some average, for example. This is called a random forest. You may have heard of. Another idea is you put them in series. So you have different ones that are maybe not all perfect, but in a series, they become actually very strong, a very strong model. These are called boosting models. Okay, that was one type of model that is used a lot in our community. My colleague Saya Samanipur uses them, for example, in analytical chemistry and chemometrics. What about neural networks? Well, as the name indicates, they are inspired by neurons. So here's a picture of a biological neuron, or 2 neurons, as they are in the brain. They consist of this cell with these actions that then have all these synapses, right? And I have to look this up, of course, but there's about 86 to 10 to the 9 neurons in a human brain, and each neuron cell has then 1,000 to 10,000 synapses that connect to other neurons, right? So these are all the connections, and when you learn, you make those connections, right? So your connection can be seen as an on and off switch. So if you make a connection, then now it's on. If the connection is gone, it's off, and information can go through. Signals can go through. So if we compare this to the largest machine learning models, like ChatGPT-4 has in the order of 1 trillion parameters, which is about 100 to 1,000 times smaller than the human brain. But still, not such a big difference, right? It's larger than the brain of a rabbit, say, already. So we're getting there. Of course, it doesn't mean that if you have the same number of parameters, you're equally intelligent. That's a different discussion. Hey, some people may argue that maybe they are already more intelligent than humans, at least some humans. Anyways, this is a picture of an artificial neural network. So that's how we represent them, nodes and edges. They look a little bit like the graphs I was talking about before, where we have layers. We see them in layers. And the first layer is the input layer, so information enters there. Then we have some hidden layers that are usually not, manipulated by you. This is the part that has to learn. And then there's some output coming out. So information goes in, X goes in, and Y has to come out. And the edges represent parameters or weights or coefficients of the model that we have to learn. And these nodes represent so-called activation functions, so nonlinear functions. They typically look like such a switch function that, depending on the input, will switch from on to off, from 0 to 1, right? And then, people may talk about the width and the depth of neural networks. So the width is, how many nodes do you have in one layer? And then how many layers you have. So how many layers do you have in hidden layers is called the depth. And so a deep neural network means that you have many layers, so a large neural network. And so deep learning refers to neural networks that have many hidden layers, and many, as with physics, means more than two, actually, in practice. So it's not difficult to have a deep network. But you can have thousands of layers, right? 10,000s, even. Now, mind you, it all just represents a mathematical function, right? So in principle, you can fit any function, any high-dimensional function. I can have several inputs. So this is now a two-dimensional input, but I could have many. I could also have multi-dimensional outputs. Doesn't have to be just a scalar. I don't have one. It can be a whole vector or images or whatever. But it's just a mathematical model, and same as similar to, I don't know, Taylor expansion or whatever. I can fit any possible function. So Y, this is the output that comes from these nodes. Well, so I have a sum over these nodes, 3 nodes. That is a weight. Well, we see here the 3 edges, and each edge I told you is a weight. Multiply these activation functions, which is, F2. 2 stands for the second layer. And then what goes into each of those? Well, that's the part in the brackets here. So again, each weight is a sum over the weights over the nodes in the previous layer, right? So this one gets 3 lines in. Each line is a weight again, multiplied by this switching function, which is, of course, the switching function of these nodes. And also these nodes, again, are determined by an input, which, again, is in these parentheses, which is then the sum over the input nodes. So we have 2 input nodes here. So the input here, X, is the input, which is multiplied by a weight that arrives here, etc., etc. So it's just a nested looping of functions of functions of functions, okay? So, and the more layers I make, the more nesting I get. But it's just a mathematical function that I represent in a graphical way. Okay, so it's used for classification or regression, and the goal is to learn those weights by giving many examples and tweaking those weights, right? Tweaking those weights in the mathematical expression, or the lines, the edges in the graph, to do a good job on the, let's say, curve fitting. But it's a very high-dimensional curve fitting. The algorithm is I do first the forward propagation for each data point. So data goes in, and I look what is Y, and I compare that to the target, to the label, the ground truth. What should it be? If there's a difference, then I should tweak the weights. That means calculating the derivative of that difference with respect to the weight. And so that means basically just applying the chain rule to that function there. And so go back through the nesting, and that's just called back propagation. Just means going backwards, right? And just go all the way backwards until I have the weight. I take the derivative of just the chain rule. So back propagation is just machine learning lingo for applying the chain rule to get the derivative, and then I know how to move the weight to get a bit closer to the answer, to a better prediction. So I step 3, optimize the weight and go back to 1 until convergence. Okay, pros and cons. Well, the neural networks can be proven mathematically that they are so-called universal approximators, which means you can approximate any function to arbitrary accuracy if you're willing to add enough nodes. Right? There's many architectures possible, so you can draw lines any way you want. You may skip some. You can even go backwards. Information can go backwards, so-called recurrent neural networks, which is used in language, etc. But that's another advanced course to tell you a little bit more about different architectures and their advantages. The interpretation is a bit more difficult, right? This is often seen as a black box. It's not so clear what happens in between. And if there's some prediction and you're surprised by the prediction, then to figure out why did it predict this and not that, yeah, that may be a bit more work than with decision trees. Yeah. Yes. Yeah, but there are typical choices you make. So here I draw a sigmoid. So 1 over e to the 1 plus e to the minus x, or tanh. But often they are, yeah, I mean, there's classes of functions. ReLU is a popular one, but okay, it's just a straight line, 2 straight lines with a kink in it. Often people try and see what works best. There's like 2 or 3 often used ones and see what works best for you. It doesn't matter so much. It just has to go from 0 to 1. The only problem is that if the input that arrives into the next layer is very on the x-axis, very much on to the left or very much to the right, then you're either completely 1 and derivative 0, or you're completely at 0 and derivative 0, and then it's difficult to optimize because your derivatives are 0. That's the only issue that you may want to choose for one function or another. But that can usually be fixed by, well, normalizing your data, things like this. But so the point is you take simple functions, and the idea is that it learns, in a sense, the functions, because you basically you scale those functions, right? So you have a switch function, but multiplying by the input by a weight means just stretching it, etc., or making it steeper or less steep, and then you multiply by a function means you stretch the y-axis, etc. Yes. They don't have to be nonlinear. They can be linear functions, but that means the whole model will be linear, and that it makes the whole thing, yeah, maybe too simple for your problem. And neural networks are good because you can fit very complex things, and yeah, so that's where the nonlinearity comes from, because the rest are linear operations, just summations and additions. Yes. Yes. Yeah, and Robert will show you some examples. Yeah, you don't have to code this up from scratch. There are libraries that do this for you, TensorFlow and Keras, if you like Google, or otherwise PyTorch. Yeah, and if you like to do that, come to my machine learning course, actually. That is in April and May. I'll teach this, and you get to code yourself.
A similar question, which is, do we have to create mathematical models to create the models? Or do we need the coding skills to create the models and these architectures? Or do you mainly use existing mathematical models?
Well, depends what you want. And again, I think Robert will tell you more about it. But I think for us, generally, yeah, we don't code this up by hand. It's just nice to know what happens under the hood. But we, download a library, and then we just have to talk about so-called hyperparameters, which are the parameters that define these things. And what are hyperparameters? Well, the things that you don't learn. So how many nodes should there be in a layer? How many layers? Which activation functions do I want? Maybe just sigmoids. So you just decide a few things, like tells you basically how complex is your model going to be. And then you feed it the data and you see what comes out. And maybe you tweak a little bit with the size of your model and some other things. But in general, yeah, you're not going to code up this whole thing from scratch. So there's very nice Python libraries for you that do that. I hope that answers your question. Now, if you want to invent your own new machine learning algorithm, then yeah, that means really going in and maybe coding up your own and see how you can change things. Yes.
First, person, thanks for the answer.
Okay.
I'm satisfied.
Very welcome. Oh man, I'm
And then someone
running out
said,
of time.
in science, when you make such predictions, you need to back it up with logic, right? How do you trust this black box far away?
Excellent question leading to my next slide. Thank you so much. Okay, so how about training, and in particular, how about validation? So now we have decided about our data, we've decided about our task, of course, we've chosen the model, and how are we going to train it? So suppose here we have some data, and now I want to use this to train a model that then can do predictions for new data. And here I took as an input feature, let's say, polarity of the molecule, right? Which is probably very naive, but it's just an example. I could just fit it with a straight line. So I have a very simple model, just a linear model with two variables, the bias and the slope. And then my model will predict for those polarities, some probabilities that lie on that line. And well, obviously this is not the best because there's some discrepancies between the green points and the red, the green circles and the actual data, which are the blue stars. And so how can we measure how good our model is? Well, we need to calculate the error, basically, of our model, right? This is called a loss function in machine learning lingo. And this is one that I think all of us have used because it's the least squares method, right? So I can just compare the model predictions, y. So that's my representation of my model. Remember the representation I showed as for the neural network, right? So I can just plug that in there, y that takes as input x, and of course the w's, the coefficients of the parameters that I learned and want to learn, and t are the targets, the labels, right? The ground truth is called. So that difference between y and t are represented here by the red lines, and the squares of those I want to minimize because I want to have the error as small as possible. So the sum of the square red lines, right? And so then I can plot it and see how that goes if so it starts with a high error, and then when I try to minimize that, my error will go up and down, but I stop when it's minimal, and some of these squared red lines is minimal. So let's have a look at a simple example, another simple example. So here I took some data that came from some measurement for which, let's say, I know the function, although in general I don't know the function. It's nature, and but let's say it's a sine, which is a dotted line, but in general I don't know this. But maybe I generated some synthetic data, so actually I know how I generated data. I just put some noise in my sine, and that gave 10 points. And now I want to learn to train it with a model, not a neural network, but an even simpler model. Let's say I take a polynomial, right? So this is my polynomial, which I stop at some order m, and my m determines then the complexity, right? So if m is a large number, I can have a very complex number. I can fit very complex functions. So let's start with m is 1. So now I have only w0 and w1, only two parameters. I can only do a straight line, and well, that's clearly a little bit of an underfit. It's not too bad, but it doesn't really capture my ground truth function. If I make the order a bit larger, actually already at m is 3, it's not so bad, right? It's not spot on my dotted line, but it captures the essence of the function, the underlying function. So that's really nice. I can keep on going, but then you may get stuff like this. So this is at m is 9. And you see, actually it goes through all the points, my model, my green model, but it's fluctuating a lot. Okay, now if I plot it again, now my loss function or my error function, as a function of the complexity, you'll see it goes down with complexity. In fact, at the end, the error is 0. So fantastic, right? I mean, the error is 0. What more do you want? Because yeah, it goes through all the points. I'm predicting all the points perfectly. Still, that may not be the model that you want, right? It's called overfitting. This is clearly an overfit because basically I'm fitting the noise, right? I'm going through all the noise here, and that's not really the underlying physics. The other side is called underfitting. So what do you do? What can you do? The question, of course, is what is the predictive power of these different models? So if I would now take new points that I have not used for my training of my model. So not those 10 training points, but now I want to do predictions. So I want to use unseen data. How well does it predict? Well, in general, what we do in machine learning is we split beforehand our training data in a part for training and a part for validation. And that part for validation, we put in a locker and we lock it up. We're not allowed to look at it anymore. So it should not influence which model we choose and how we do the training, etc., etc. It should not influence it. And we want to do this double blind, so okay, you cannot see that part. And then we train, and then we do the validation with that data after training. So let's do that. So we just choose some points in between the blue points. Well, the first model is, of course, not doing great. I mean, some points are close, but some points are completely off. The second model is doing pretty good, actually. The red points are quite close to the blue points, so that's great. But here we're completely off, of course, because due to these fluctuations, the error is very large. So we can also now compare, we can make a validation. So we calculate the error for this, data that we kept aside. And then actually, yeah, it goes down first with complexity, but then if we make it more complexity, the error goes up again, right? And that's, of course, suspicious. So we don't want to be in this overfitting regime where the validation error goes up. The optimal point is actually where the validation error is minimal. And we should choose a model that has that complexity, okay? Because otherwise we are overfitting, we have fitted the noise, and our model is too complex for the data that we've seen, and it will not have any predictive power. This is a very important rule. Split your data and check. And I think that's probably more general than just machine learning. And any time that we fit to training data, this should hold. This is a famous quote from John von Neumann. With 4 parameters, I can fit an elephant, and with 5, I can make him wriggle his trunk. Of course, in machine learning, yeah, we are not thinking like John von Neumann. We love parameters. The more, the better. And we have, thousands or millions of weights and parameters that we fit. So bye-bye, John von Neumann. In general, we will have too many parameters, often more than data points, right? So there's always the problem of overfitting, right? So, I mean, neural networks are very large, and there may be many parameters. We can fit anything, so how do we avoid overfitting? Well, you should do validation, obviously. But then what can we do? So in the case of underfitting, so if we have underfitting, the solution is increase the model complexity, right? Make your neural network larger or whatever, add more parameters, or decrease regularization. I'll explain in a second what is regularization. If we are in the overfitting regime, it means we have a large variance, so there's large fluctuations, right? Decrease the model complexity, so make it less complex, make your neural network smaller maybe, or add more data. So this is the example here. Like if you have many parameters, okay, you need also a lot of data. So if I have a ton of data, then even at n is 9, I get a very reasonable curve. Okay, but often you don't have more data. You would have used all your data, obviously. But then there's this other solution, add some regularization. So what is regularization then? Basically, you add an extra term to your loss function. So mind you, the first term is again our least squares method there. But then there's a second term here, and that just is the sum over the weights squared. So if the weights take very large numbers or very small numbers, so they're far off from 0, then the square, of course, will be large numbers, and my loss will be large. And so what does that do to my weights? It will keep them small. It regularizes the weights to not take exotic values, and that is, in practice, avoids very much overfitting. You can steer how much regularization you want with this hyperparameter lambda. So if lambda is a large number, you'll do a lot of regularization. And so if lambda is very large, of course, this second term completely determines your loss. And it really just all it tries to do is keep the weights small, keep the weights all close to 0. And then, of course, you have a model that doesn't do anything because all the weights are 0, so it doesn't work. If the lambda is very small, let's say 0, then you don't do anything. So maybe you're overfitting because now you have a very fluctuating model. And so you have to play a bit, right? Should not be too large, not be too small. to avoid overfitting, which you can check with your validation. Okay, that is what I wanted to tell you. The overall flow of a setup of a machine learning model, where, yeah, having decided your task, you have to worry a little bit about your training data, always do an exploratory data analysis, and think about what is the best molecular representation that you can use for your task. Choose a model, and then by the training, always split your data in training and validation. And you may want to define a loss function and use regularization to avoid overfit. And then we're going to see some examples on how we then use it for predictions in the next part of the talk. We already had some questions in between, and I'm already a bit over time, so maybe I stop here. Maybe there's questions more at the end, but then I give the floor now to Robert. Yes. If you want, I have two parts in my section. If you want to follow it on the laptop, you can, but you don't have to. My session will be via Google. Well, I use Google Colab. I will provide two Jupyter notebooks. Everything's there. You just need to run it, and it should do everything without errors. At least in my hands, it did that a few days ago. So I hope it'll be fine.
And I cannot hear you.
Oh, yes, of course.
Audio. Can you hear me now online? Okay, so also for the people online, in this session, I provided Jupyter notebooks that's in principle pre-coded. You can follow them. The first part will be about Bayesian optimization, and you can follow everything if you look at this QR code, which will give you a link. You probably need to download the notebook or copy it and open it again, because I didn't make it editable, because you could edit everything that I do, and if you put in errors, then nothing will work. So please, you can download it and open it again for you. But if you do that, you can follow everything that we will do today. And maybe I can put this down. And so if you've never seen Google Colab, this is Google Colab. It can run Python code. It can actually also run, let's say, other stuff. You can install things yourself. You see, I wrote a lot of text, which I will not comment on everything here, but this first part is about Bayesian optimization. And one of the questions before was already, when you do machine learning, are we going to code everything up? The normal answer is no, because we're probably not the best software engineers. There are much better people in software engineering that optimized everything. They have done this for us. So for instance, here, if you run this code, we need to install a library that runs Bayesian optimization. And in Google Colab, you can run the command pip install Bayesian optimization, and then click on the play button to the left. And you see the very first beginning, it takes a while to start, but then it downloads everything. So you see it's downloading a few things, it installs them. And when it's done, it installs, successfully installed. And then you see this green tick on the left, which says it ran the code. So this way, we have installed a package that can run Bayesian optimization. Now, the next code cell is a bit, let's say, specific in coding. Like the way it works in Python is we need to tell Python which packages we need to use. And in this specific example, I use some standard packages, NumPy, Pandas, scikit-learn. I use the Bayesian optimization one that I just downloaded. And I use matplotlib, which does some plotting. So what this does, it imports these packages to the environment, and then we can use them in the next codes. So again, I click on the left, on the play button, it runs in 2 seconds, it should run and then complete. So now we have everything loaded. But before we do like actual things, like we heard from Bernd before, the first thing is always define the task. In this section, the task will be optimizing reaction conditions of a Suzuki-Miura reaction. So if you followed my lecture, yeah, Suzuki-Miura is a popular reaction. The good thing about it is there's a lot of data out there, and I can emulate an optimization based on a data set. And you will see in a minute what I mean with this. Okay, there's a question. Oh, a camera, yes, of course. So, yes. I think now my camera is there. Okay, so now you can also see me. Okay, so, and we base this example, so the task is optimizing Suzuki reaction. Normally you would do this in the lab, but you will probably see that we're not doing any experiments here, so we'll not do experiments. What we'll do is, there is a high throughput experimentation dataset on Suzuki coupling that you can download online. It's part of another package called Olympus. And we can use this package to fit a model. And it's a different model than the one that Bernd discussed. It's called Gaussian processes. And this model then predicts for different reaction conditions what would be the yield that were observed in the experiment. And this is then our emulator of an experiment. So when the model is supposed to, let's say, okay, now we do an experiment, we run this model to tell the outcome of the experiment. So in real life, you would go to the lab, run a Suzuki coupling, check the yield, and then tell the computer that's the yield. But in this demonstration, we'll just use a model to, let's say, emulate this experiment. Okay, so we want to optimize Suzuki coupling with Bayesian optimization. So what actually is Bayesian optimization? So we heard before it's similar to reinforcement learning, but it's not. So let's say in a very brief way, it's an optimization algorithm. So it optimizes something. And maybe you know that some optimization algorithms use the gradient. So we heard that before. Machine learning models are often trained with gradients. But Bayesian optimization usually doesn't need a gradient. And that's why it's often called a black box optimization algorithm, meaning that you don't need to know anything about how your process works, but you can still learn the relationship between input and output, and then use it to find the best input that optimizes your output. And the way it does that is by 2 means. So in the plot that you can see here, you have the red curve, which would be let's say the perfect relationship between input and output. So input is on the x-axis, output is on the y-axis. So for instance, in reaction optimization, the input could be the equivalence of palladium catalyst that you use, and the output would be the yield, which is on the y-axis. And red would be what would be the perfect relationship. The green curve, this is the model that Bayesian optimization learns to approximate the relationship. So what Bayesian optimization does is it continuously learns and improves a model that tries to predict the objective from the input. And you see here at iteration 3, it does not really know the shape, so it does not reproduce the red shape well enough. And there is a second thing that Bayesian optimization does. It not only estimates what is the predicted, let's say, yield, but it also predicts what is the uncertainty, like how good do I expect my prediction to be? And this is the green shaded area here. So this means that when the green shaded area is very wide, it means the model knows that it cannot predict the yield well in that region. And this is said to have a high uncertainty. And as you can see, if we go from iteration 3 to iteration 5 to iteration 7, not only does the green shape get closer to the red shape, you can also see that the green shaded areas, the uncertainties, are much smaller. So the model knows that it can be more confident about its prediction. And what Bayesian optimization does is it translates these things, how well it predicts and how uncertain it is, into something that's called an acquisition function. So what this basically means is the blue curve tells you where should you do your next experiment. So if the blue curve is very high, it means this is where I'm either very uncertain or this is where my yield will be very good. And it means that this is where you should do your next experiment. So for instance, after 3 iterations, apparently, if you're here to the left, this is where you should do the experiment. And you can see that then in iteration 5, we have a data point at that point. And that turned out to be actually very bad yield. So in that sense, well, we were very uncertain about it, but it turned out it was not a good yield. And then what this acquisition function, then it changes such that it narrows in on the optimum. And you can see in iteration 5, it now gets actually sample closer to where the optimum of the function is. And then at iteration 7 in this example, it really knows quite well where is the optimum of my sample. So that's in a nutshell Bayesian optimization. So the data set now that I have is 247 experimental data points. They were done with high throughput screening. It's a Suzuki coupling that's shown here in this reaction scheme. We have a halide with a tetrasol group. We have a boronic acid ester that's a bit electron deficient. So what is held constant is the equivalent of the halide, but the model can vary the equivalence of the boronic acid ester. It can vary the equivalence of the palladium precatalyst. It can vary the equivalence of the base, potassium phosphate. And it can vary the temperature, but we keep the concentration and the solvent the same and the reaction time. And this is the desired product. So this is the problem and the data set this is based on. So as I said, for this example demonstration, we just download the data set. For this, we use a program called wget. And if you look at the link, this is downloaded from a GitHub repository. We downloaded the data. And what we next want to do is we want to read the data into Python and look at the data so we understand what's going on. So what I did in this line was I read the data as a CSV file. I defined what are the names of the columns. And then what you see here in this cell is it's a part of the data that's printed. So you can see you have different columns and different, so you have 247 rows. The first column is temperature. So it starts at 75, at the end it's 90. We have the mole percent of palladium. So we start from 0.5 mole percent to 5 mole percent. So we go quite high in mole percent. We look at the equivalence of boron from 1.0 to 1.8, and you see it varies a bit. And we do the same for the base. And the final column is the yield. And you see that at the end, there are some lines that have quite high yield, almost 97%. In the beginning, there are some lines that have only 2%, so not very high. So this is the data that we use to emulate the experiment. And now, so this is in a way, technically this emulator is supervised learning. So we have features and we have labels. The features are literally the temperature, the palladium equivalence, and so on and so forth. And as we learned from Bernd before, we always need to do some data processing. So what happens here is that we scale the data. And the reason we're doing this is because if the different, let's say temperature, for instance, goes from 75 to 90, the numbers are quite high, whereas palladium equivalence is very low numbers, 0.5 to 5. If we scale the data, they're all on the same scale. And this makes it easier for the model to learn the relationship between the different results. So what this code cell is doing, if I run this now, it scales all the individual parameters such that it's in a range between 0 and 1. This is defined here. So if you want to learn more, you could Google this min-max scalar function, which means that the minimum of the data is 0, the maximum is 1, and everything in between is just based on that. And we can see what happened there in this. And now there's a question.
Yeah, they say all the future inputs are continuous. What would I do if I had inputs that were both continuous and categorical? Could I still use Gaussian process regression?
Yeah, that's an excellent question. The answer is yes, but you will need to come up with a way to translate your, let's say, categorical input into a numerical way. So, I mean, you could do this simply, okay, if it's a category, it's a 1, and if it's not, it's a 0, so binary. But there are other ways to do this. And there are also Bayesian optimization algorithms that natively deal with that. And I think even this package can do it. So yes, definitely you can do it. And you could do it in an easy way or in a native way. But the easy way is just, okay, if it's a certain category, yeah, it's a 1. And if it's not, it's a 0. So that can always be done. But it's an excellent question. So what I see here is I printed the data again. And what you can see here now that the temperature goes from 0 to 1, the palladium equivalents go from 0 to 1, the boron goes from 0 to 1. So now everything lies between 0 and 1. That's what we just did. We scaled the data. Okay. Now, as I explained before, because we don't want to do experiments in the lab in the course of this crash course, what we want to do is fit a Gaussian process regression. And this can be easily done via the scikit-learn package. And this is done in this code cell. And for doing this, we first need to provide the data in a certain shape. So first we need to reformat here. This is done in this line, where we just concatenate the different columns of the data into one, let's say, big matrix, a big table. And we need to do the same for the output, the yield. And then we define a kernel. So basically this is something very specific to Gaussian process regression. I don't want to go into too much detail, but the kernel is something that's very important for Gaussian process regression, similar to how in neural networks from before, for instance, activation functions are very important in modeling the nonlinearity of the system. So this line defines now my emulator. So my thing that should emulate my experiment. And this is when I fit the model. So this single line creates the fit. And what I can do is I can use this emulator to predict the outcome of the experiment given an input. And this print just shows how I reformatted the data. And you probably are interested in how good does this model predict. And this is why I now create a plot in the next code cell. This plot shows the experimental yield on the y-axis versus the predicted yield of the Gaussian process regression. The blue points are the predicted points. The lines that go from left to right are the predicted error that the model has, because Gaussian process regression always gives you an uncertainty. And what you can see is if any point is on the black line, it would be a perfect prediction. If it deviates a bit, it has an error. But I would say, given that we actually didn't do much about feature engineering or any other hyperparameter optimization, the model represents the trends in the data pretty well. And the idea is that this model now serves as our replacement for the experiments. Because what we actually want to do is we want to do Bayesian optimization. And for that, for any optimization, we need an objective function. This is defined in my next code cell. For our case, it's very simple because I just want the objective function maximize my yield, give me the highest possible yield of my Suzuki coupling product that I can have. And here I just basically redefine making the prediction with my emulator as my objective function. But the objective function could also be you run an experiment, you measure the yield with HPLC or GC, you integrate the peaks, and you get the peak area as your outcome. So this is just then defined in a convenient way. So Bayesian optimization can make use of this objective function. Okay, so here is some text defining the task. This lines here defines the optimization space. So because here we are limited to the data set that I started with, and the data set only has temperatures between 75 degree and 90 degree. And I define those ranges. In Bayesian optimization, usually you want to tell the model what is still an allowed parameter. So am I allowed to run the reaction at 75 degrees? Well, in this case, yes, but if it was 74, you would not be allowed in this case. And if you run an experiment, those bounds could actually be the limits of what you can do experimentally, because maybe you have a solvent. I think we used isopropanol, and maybe you don't want to run over the boiling point of isopropanol, or not too much higher. I think this is already a bit higher than boiling point, but maybe you don't want to run the reaction at 150 degrees Celsius, and you need to tell the Bayesian optimization model that this is an allowed parameter range. For palladium, we have this range, anything between 0.5 and 5 mol%. Boronic acid ester, anything between 1.0 and 1.8 equivalent. And potassium phosphate, anything between 1.5 equivalents and 3 equivalents. And the way we define this in our case, because we have scaled data, is that all parameters can go from 0 to 1. So remember that we scaled the data that the minimum value starts at 0 and the maximum goes to 1. Basically, we just now need to tell the model, don't go lower than 0 and don't go higher than 1, and then we fulfill these bounds. The other thing we can, for instance, define is how many iterations do you want to run the Bayesian optimization. So Bayesian optimization is an algorithm that runs through loops. So it says, here, run this experiment. So it tells you, for instance, run at 75 degrees, use 0.5 mol% palladium, use 1.0 equivalents boron, use 1.5 equivalents of base. Then you run the experiment, measure the yield. You tell the model this is the yield. The model will use this data to update and make a new experiment. So that's then the iteration 2. And you need to tell the model when it should stop, because in principle, it doesn't know. It will go until infinity. So you tell it here that after 20 iterations, we want to stop. So this is basically, we define how long we want to run, what are the parameter bounds. And what we do here is we provide a starting point to the optimization. So the idea is if you run the experiment, probably you have tried this experiment before. So maybe we started at the temperature of 75 degrees. We started at a palladium amount of 0.5 mol%. We started at 1.0 equivalents of boron, and we started at base. So we all started all parameters 0, and this is what we do here. So, and then we provide the yield to the initial, and we have an initial point. So this is the starting point of your optimization. What is maybe you have a known data point, you provide it, how many iterations, what are the ranges of allowed parameters that, let's say, you can probe experimentally. And this is everything you need to do, because the next thing is already the Bayesian optimization. So what we do is we define the Bayesian optimization here that uses the objective function with the parameter bounds that we defined. And in this case, I say verbose 0, which means it shouldn't print a lot of things that I don't want to know, because I print the things that I want to know later. What this line is doing, it tells the model the initial point that we already know. So it registers the initial point, and then it runs the action optimization. And because now we have this objective function on the computer and don't need to run the experiment, the loop runs internally and basically completes the entire optimization very fast. So if I run this now, it's already complete after 5 seconds. And what you can see here is you can follow the progress that the model took. So the first data point was 75 degrees Celsius, 0.5 mole percent, 1.0 equivalent boron, 1.5 base, and the yield for that was 3.7%. The last column gives the best yield encountered until that point. So at that point, it's 3.7. And if you now follow through iteratively, you can see how the model quickly learns that it needs to increase the temperature. Basically, in this data set, which is a very simple data set, it needs to increase everything to get to good yields. I mean, not to the maximum value, but somewhere close to the maximum value. But you can see actually that in this case, already after 5 iterations or 4 iterations, the yield that it ended up with is 72%. I will admit that this is a very simple data set, so it needed very few iterations, but it did learn very quickly what it needed to do. And if you want to plot what the model, how the model progressed through the data, you will see this here. On the y-axis, you have the reaction yield, and on the x-axis, you have the iteration number. We started a very low yield. The red line shows the current proposed experiment, and the black line shows the until that point best yield. So you can see in the beginning, it quickly realized that it need to increase the equivalence and the temperature to get to high yields. And then at the end, it really fine tunes a few of these parameters to narrow in on the maximum point. And this is then the Bayesian optimization. Now, you might think this was a bit too easy and I could not really use this in my lab, well, because it ran everything internally. But to do that, I gave you a second way of run this optimization, which is explained in the next part of the code cell. And this is doing this step by step. So there are basically 6 steps at every iteration that you need to follow. The first step is you use Bayesian optimization to propose reaction conditions. The second step would be you perform the experiment in the lab and provide the outcome. In the notebook, I use the objective function, but in the following code that I will show below, you could actually just enter the number that you literally measured in the lab and run the code cell, and it would work. The third, that's the third part, when you provide the outcome to the optimizer and register it with the register function. Then you can print the optimization progress so to know how it's going, but technically this is optional. You can illustrate the optimization progress with a plot. It's also optional. And the last step, you go back to point 1 and propose new reaction conditions. So these are the steps that you would need to do if you want to run reaction optimization in the lab. So let's do these steps. Before we do step 1, we define our Bayesian optimization function. The main difference now is instead of giving it an objective function, we say here none. So in Python, there is no explicit function, and this is because we provide the outcome as a number. However, the parameter bounds are still the same because we still want to optimize in the same temperature range, in the same equivalent range, in the same catalyst range. So this is, again, you will need to define that. And here for reproducibility, you can also define the random state. So this means if I rerun the same optimization, give the exact same proposed parameters, then this does that. You don't need that technically, but it's sometimes nice for demonstration purposes to do that. Yes, there's a question. So the question was whether the parameter bounds serve as priors. So not really. So in a way, they tell the model how far can I go. I mean, in a way, they probably used. It depends a bit on the Bayesian optimization algorithm, whether they're used or not. They don't need to be used. They can be used. And I don't know now because I have a default. I didn't like I use default settings. Like here, I will. So it can be used, but it does not need to be used. It's more like if I propose a new experiment, what is a valid experiment? Basically, that's why you need to define the parameter bounds mainly, because otherwise it will propose, oh, run the temperature at 100. I'm like, yeah, but no, I say until 90. So that's the idea. So in a way, you want to avoid that the computer tells you to run an experiment that you cannot run. That's the main idea here. But it was a good question, and it's a common question. Okay, back to the code cell. So what this code cell does is defines the Bayesian optimization algorithm and registers the initial experimental results that I have. So again, I use the register function. And this is now when we can enter the loop. First step, use the Bayesian optimization to propose conditions. This is done in the following cell. There is the suggest function, which proposes a new experiment. This is the proposed experiment. However, now we scale the data that it's all between 0 and 1, but this is not the actual, let's say, range that I use. So what I do is I transform the data into the original range and then print it into a nice text that a human can read. So the output is the next experiment to perform is temperature 90 degrees, palladium amount 5 mol%, boronic acid ester amount 1.8 equivalents, potassium phosphate 3.0 equivalents. So now you could go to the lab and run this experiment. I'm not going to do this here. So what I do here is I say run the objective function. But if you, instead of this objective function, all right, so I could now, for instance, okay, apparently I cannot type. I can type. I could now write, oh, my yield was 0.5. You could write that because you went to the lab and measured the yield and run this code cell. This will work. But yeah, I don't want to do that now. I want to still use the objective function. But if you want to use this in the lab, you can. You would just run it with the value that you provided. And then, yeah, the yield of the proposed experiment is 0.88. So in this one, we were actually very lucky. It already identified quite good conditions on the first guess. And the third step is you need to tell the model the outcome of this experiment. And this is this register function. And you see what it does is it uses the proposed experiment and the experiment outcome. It registers it to the Bayesian optimization. Next step is print the results so far. So you will see in the table, I have the first initial experiment that I provided and the first one that I now performed in the lab. Not really, but you can, I guess, imagine. We can print the optimization progress until now. So this is now the most boring graph ever because it has the 2 points, line between 2 points. And then step 6, go back to point 1 to perform another optimization cycle. So in this code cell, what you do, you scroll up until you are at the suggest. So you run the suggest. It tells you the next experiment to perform is 76 degrees Celsius, palladium amount 2.83 mol%, boronic acid ester 1.36 equivalent, potassium phosphate 1.52. So you go to the lab, run the experiment. So what I do is I run the objective function, but you could again go here, literally write the value that you recorded experimentally in this code cell, play. And let's say here the yield was 15.9. Oh, we got worse again. So I register this to the model. Now it knows the outcome. You print table, you see the 3 different results. You plot them And you see it went to a bad territory. But because we only have 3 data points, it doesn't know the space yet. So it wants you to explore a bit. So that's why it goes now a bit back and forth. And now, next point, we go back to step 1 and again need to suggest an experiment. And maybe at this point, it already got boring to you, but let's do it one more time. We suggest an experiment. Next experiment to perform is 90 degrees, palladium amount 1.22, boronic ester 1.79, potassium phosphate 2.98. We perform the experiment, so we go to the lab, run it, type the result in here. It's 64.5. Yay, it got better again. You register it, you print the result, and you plot the outcome. And yeah, it's getting better again. And you see, I think at this point, you probably are really bored with this because it's really just always the same. But this is how the Bayesian optimization loop would look for you in the lab. Like everything you need to do is, in a way, you tell the model what are my allowed parameter ranges, define the model, maybe tell it if you know some initial experiments, tell the outcome of those experiments, and then make the first experiment to suggest. And then you can go to the lab, run the experiment, and enter in this closed loop optimization workflow. Yes, there's a question.
I assume that you can also update the model with the data points that you generate.
Oh yes, that's a very good question. So the question was, I assume you can update the model with the data points that you generate. Very good point, and that's exactly what it's doing. So this is happening behind the scenes, and I could visualize it, and there are ways to visualize how the model changes. So yeah, this is exactly what is happening. Okay, other question. Yes, so the question was, can I also make the model suggest more than one experiment? And yes, you can do that. And it's actually a simple option. So you can just basically say how many suggestions to do. I have to admit, I would have to look it up how to do it right now, but it can be done actually quite easily. If you want to be brave, you could probably try if GPT-4o knows the answer. You could probably provide the code, hey, can you change this code to give it a batch size of so and so, or do 10 experiments? It would probably know how to do it, but no guarantees. So, but yes, it's very easy to do that. It's very common to do that, and it could do that. Yes. Pardon? Ah, yes. Yeah, so basically we're now discussing different, let's say if it provides multiple suggested experiments, sometimes it uses, let's say, different models or different acquisition functions, focuses on different parts of the data. And that, I mean, that really depends on what approach you use. But I guess there's another question.
How does the model decide when to explore and when to exploit?
Yeah, it's a very excellent question. I mean, in the model that I now use is basically, let's say it has some default parameters. In a way, technically you would need to suggest this. However, often these standard parameters are pretty okay in that it focuses usually a lot on exploitation, which means narrow down on the best region. Because in the end, this is optimization. You probably want to be quick there. But if you care more about exploration, then you can change some parameters such that it focuses more on that. So the package that I provide allows you to do that. But if you want to do that, just the plain vanilla Bayesian optimization that does a lot of exploitation, then the settings that are default here are good to go. Yeah. And I think in the interest of time, I will close this Bayesian optimization part, but I hope I could show you that, let's say, a very relatively simple Bayesian optimization can be implemented in very few lines of code and with existing packages. And if you actually followed the QR code, you can download it and run it in your own lab. And then you have no excuse to another colleague, why didn't you run Bayesian optimization? So technically, you're like, well, okay, I could have done it. But anyway, second part, supervised learning, same as now. You can follow this QR code to download a Jupyter notebook. And you'll follow a lot of the steps that Bernd was teaching you in the first half of the lecture. Because we're really gonna follow through with all the steps that were mentioned. So, I mean, okay, that was step 0, which was task definition. I will define that for you. But the rest we'll do, let's say, exploratory data analysis. We'll do some feature generation. We'll do some model selection, model training and prediction. Okay, so crash course supervised learning. And Bernd was already telling you about some packages that we use for machine learning. My personal favorite is PyTorch. It's also used a lot in research applications. So a lot of people that use code, let's say that custom made or let's say custom implementations, they use PyTorch. And you can see that if I run this code, the first code cell, it installs this. It actually takes a bit, not too long. It installs PyTorch and installs RDKit. Also, RDKit was mentioned by Bernd. It's a package for cheminformatics. It can deal with smiles. It can deal with other representations, graph representations that we heard about. And again, the next cell imports everything we need to the environment, a lot of things in this case, because we need a bunch of packages, we need RDKit, we need, again, scikit-learn, we need PyTorch, and we need matplotlib for plotting. And this will take a while. And in the meantime, I'll explain the task. The task will be predicting the pKa value of organic molecules. This is based on a data set that comes with the program Datavoria. This is another free cheminformatics program that you can download. However, the annoying thing is that the data set just is part of the full program, and I don't want to download the full program. So what I did for this exercise is I put this data set on my Google Drive and then download it from there. So this is what I do in this code cell. I download this data set through Google Drive. It's called data.txt. It downloaded it. And I again read it and then I print it just like I did before. And then we can actually see what it does. Now you see the first column is the pKa. Second column is it basic or acidic? Because the data set contains both, let's say, acidic groups, acidic molecules and basic molecules. It then has the smiles, and we heard a lot about smiles, and we'll use that as a starting point for defining our model. And then also Bernd mentioned something, sometimes you get these NANs in your data. So here we actually have a last column that's a bit weird because it's unnamed and it only has not like NANs. So NAN stands for not a number. It's not useful stuff. It's basically a column we don't need. So this is something we need to, in a way, get rid of when we do data processing. And this is something that's very common when you do something like this. And we do this data processing here. And here in this code cell, actually, we do multiple things. So first, we want to train a model that predicts the pKa of organic acids. So what we do is from the data, we only select the acidic parts. And this is then you could now say, there was this question in the session before, what about data manipulation? My answer to that is if you provide all details, what you did openly, I would say it's data processing. If you hide what you're doing, it's data manipulation. I would say that's an easy way of distinguishing. If you don't tell people what you're doing, it's data manipulation. If you tell everybody what you're doing, it's just data processing. Because processing is reproducible, manipulation is not. That's what I would say. And if I say, well, I want to make a model that trains on acids, well, if I only select my acid data, I think it's fine. I tell people that's what I do. People can reproduce it. All is good. The second part is I read out only the columns that I'm interested in. And the ones I'm interested in for now is the SMILES, which defines the molecule, and the pKa. And that's everything for now. And the last thing is, again, it could be something. Well, the last thing is I just want to read out the range, and this will be something that will become relevant later. So for now, I'm not doing any processing. So when I run this code cell, the data that I get looks as follows. I have more than 3,600 examples. Every row has a molecule defined as a SMILES and a pKa value. Okay. The next thing is something that Bernd said. Also, sometimes in exploratory data analysis, we want to visualize the distribution of the data. This is something that's often done with so-called kernel density estimation. So this is in a way fancy lingo for a continuous probability distribution. So basically I want to see what is the probability that you will find a data point in a certain range of pKa values. So this is shown here. So basically what this plot shows is on the x-axis the pKa value, and on the y-axis it gives you the probability density. If you know a little bit about statistics, you will know that the probability density is defined that the area under this curve is 1. So the probability to find the pKa anywhere is 1. So this is the range. And it tells you that, for instance, in this data set, there are 2, let's say, maxima of peaks. And maybe if you're an organic chemist, you might have an idea of what these peaks could be. So there's a peak at around, I would say, pK of 4. And this is probably carboxylic acids in a broad sense. And then there's another let's say, broader range at around 9 to 10. And this might be aromatic alcohols or phenols. Might also be a few different ones, but I would say those are probably good guesses of what these, let's say, organic acids would be. And if you look at this data very carefully, you would also see that there are actually some, in a way, outliers, or let's say extreme pKa values. So there are some pKa values that are lower than -5, and which is extremely strong acids. And there are some data points that are above 15, something that an organic chemist or a chemist probably would not even call an acid, but they're in the data set defined as acid. I actually, before doing this demonstration, I tested around a bit. And if you try to train a model on the full range, the model will, like a simple model, will actually have some troubles with predicting these extreme ranges. So what I then say, and again, because I tell you openly, this is not data manipulation, this is data pre-processing, because I tell you, what if I want to have a model that predicts pKa values of organic molecules in the range between pKa 0 and pKa 50? If I say this is what my model is capable of, then it's not data manipulation, then it's just data processing. And so what I do is I only select data points in this range of pKa values. So if I do this in the following cell, what you see is it only removes a very small number of rows. So it removes, let's say, 60 or so molecules. So not a lot. I still have almost like more than 3,500. But what this does is then the model, let's say, it makes the task easier for the model to focus on where most of the data set lies. Because sometimes if you want to make a model that predicts, let's say, extreme ranges extremely well, you might you will end up overfitting, or you will, let's say, end up a lot of model engineering for, let's say, something that was not, let's say, very productive to begin with, because there were not a lot of examples anyway. So this is what I do. And then comes the part, I think in the code, this is one of the part that takes a bit longer. I said the data set provides SMILES. However, if you use SMILES directly as a representation, you need very specific classes of models. They are called recurrent neural networks, for instance, that can easily deal with that. And they have some disadvantages, are a bit, let's say, harder to train. But what I can do is, in our RDKit, I can use the smiles. So in this cell, I read in the smiles as a so-called mole object, which is basically the molecule as a graph, and it understands the atoms in there, the connectivity. And based on that graph, I can generate molecular descriptors. So molecular descriptors are simple properties that our RDKit predicts, and it can be as easy as, does this molecule contain a carboxylic acid group? It can be something like the estimated octanol water partition coefficient, or the topological surface area, or whatever. Like, there are a lot of descriptors there. And it's even the molecular weight. And what I did here, I printed some of them. And you can see here in the columns, it tells you the name of these descriptors. And then for each of the molecules, it gives a numerical value. It has a lot of them. It uses also molecular weight. So if I scroll down here, it has 210 of these descriptors. And this is all generated by our RDKit based on smiles. So this is, in here, what I did was feature generation. I generated features that I will use as input for my model to then predict the output. Now, there is something, when you do the feature generation, sometimes the feature generation fails. And this is actually what happens. And what you then need to still do is remove the features that have values that were not a number. And this is done here. So actually, some of these columns that were provided were not meaningful. And if you run this code cell, what it does, it removes them. And what you end up with, instead of 210 columns, you end up with 198. So it removes 12 features. If we continued with those features, we probably would have gotten a model that gave you nonsensical results, because you put, I guess the lingo garbage in, garbage out was before. Because if there is not a number as an input, the model will really, in a way, break down. So you don't want that. So even after doing feature generation, you still need to see, is what I'm doing useful? Okay. Actually, at this point, I thought maybe it's nice for people that find this coding a bit abstract, what are actually some of these molecules. If you run these code cells, it will always visualize random 6 molecules on a grid. So you see, for instance, some molecule here. So indeed, there's some carboxylic acids, we have some oximes, some phenols, some protonated amines. And if you run this code cell again, it will actually visualize 6 different random molecules. So here we have even quite some sophisticated organic molecules, but this is a carboxylic acid. Some larger molecules as well. The next code cell is something that's not necessary, but it's always nice for demonstration purposes. I set some random seeds. And this means that when I rerun a code cell, it gives me the exact same output. This is something that you want for debugging when you develop a model, when you're not sure that your model works. Because you don't want to, say, rely on luck to give you always a good, or always sometimes a good and sometimes a bad outcome. You just want to see, does my code run without error? If I change something, what does it change? So in a way, you want to be reproducible. I mean, obviously it's not something you want in the end, but when developing a model, sometimes it's good to do that for debugging. And then a figure that I think will be very useful, maybe as later reference, the full workflow of training a model. Because in the interest of time, I will not go through everything here, but this contains literally, I think, everything that would be part of such a model workflow. So you have labeled data, you split the data, you do training, validation, you do hyperparameter optimization, and you do even final training, and you have your optimized model. So for those of you that downloaded Notebook, I would say this is for later reference. Okay. Next, Bernd already mentioned this. We already had this in the previous code cell. We scale our data so they are all in the same range. And then comes when we define a model. In this part, we define a neural network. This is actually a lot of code. So if you did the details of changing the model, you would need to change a lot. So for instance, this is the part where the linear transformation happens. This is this nonlinear activation function. This is the dropout rate. And here is where we have the different hidden layers. And then we also need to define the data set because the data needs to be in a format that the model can read the data set. And we need to have a class that, let's say, collects the loss that Bernd said, like the error on the model. This is this class. And with this, we've defined all the objects. Now, everything we need to do is we need to define the training data set, validation data set, holdout data set. I need to tell what are my hyperparameters. So I have 256 hidden nodes in a hidden layer. I have 3 hidden layers. I use the rectified linear unit nonlinear activation function. I have regularization, which is dropout. So this is the part where you can change the complexity of the model. You can change the hyperparameter of the model. You can change how long should it train. Maybe I think a term that didn't fall in the last session is epoch. During one epoch, the model sees the entire training data. And you usually want the model to see this entire training data multiple times. So you saw here, I defined 100. So the model in total sees the entire training data 100 times. This is that. So if I run that, it defines all the parameters. And it actually also trains the model. So this code cell does a lot. It first defines the model, registers it, keeps track of the metrics and let's say logs them so I can print them later, defines an object that trains the model, and then actually train the model. Now, what happens in training, you can actually, in a way, follow it through here. We see we already did 30 epochs. This is what Bernd mentioned, is this back propagation part, or in a way, this loop of, let's say, I make a forward pass, I predict the outcome, based on that outcome, get the error. Based on that error, I take then the derivative, which then tells you how to change the weights and the biases, these linear parameters, to improve the loss, the error, to get lower in the loss. So this is literally happening right now as I speak. I'm already at epoch 60. So you see this relatively small model on Google Colab trains quite fast. But it's not something that happens in an instant. And the larger the model gets, the longer this takes, until the point where you cannot run this on Google Colab or your laptop anymore. You will run a large GPU cluster. You need lots of resources to run this. And this really depends on how many parameters do you have, how large is your data set, because the data set also usually needs to be stored in the memory. And all this needs to happen in the back. So you see the model gets to 100. We're already done training. It then...
So this is a relatively small neural network, only 3 layers, but it said there on top 182K parameters. So is that true? We have 182,000 parameters?
Yes, because we have 3 hidden layers. We have 56 nodes in each layer. There are 200 inputs. So I guess 200, I mean, you know, it propagates fast. Yeah. So like, I guess Bernd told you, you get to large parameters really fast. So we in an instant, we got to 100.
I'm so sorry about that. I'm so sorry. That's about that.
So we got to 100. Did the Zoom stop or?
No.
So we got very easily, we got to a model with 182,000 trainable parameters. So this is, let's say, not your ordinary linear regression that you usually do. Okay. Now this all happened in the back, but we want to see whether what the model did worked. And the first thing is always the training curve. And this is something that you saw before in Bernd's lecture. So what you can see here is the mean squared error loss, the error in the prediction, as a function of training epoch. And something happened that is very common, is that the blue curve is the training error and the orange curve is the validation error. The training error is significantly lower than the validation error. And this is in principle common. However, you don't want the difference to be too big. And I would say in this data set, we're at the borderline where probably we want to have a better model. But you will see later, it's still already a useful model, but it's definitely far from perfect. So this is not, let's say, the end of your best pKa predictor. But at least what you can see is that also the error gradually decreases for both the training error and the validation error as we go through the epochs. And at the end, we are close to convergence because the error doesn't really get much better. So in principle, this is how you should expect such a training curve to look for such a model. And then we're interested in the predictions. And this is done in the next code cell, where I print a scatter plot between the experimental pKa on the y-axis and the predicted pKa on the x-axis. The blue data points are the training data, the orange one are the validation, and the green are the holdout. So you can see the black dotted line would be perfect prediction. So you see, well, the model does learn a relationship. It tries to be close to the line, but there is quite some noise and there are quite some data points it does not predict well. So the model is definitely not perfect. And there would be more work to be done. Now, if you wanna, what you usually wanna do is then you wanna maybe, for instance, inspect some predictions and see if there are certain types of molecules that it doesn't predict well. And this is done in the final code cell. So I know I'm already over time, but so thanks for staying with me. So what this last code cell does, it prints random molecules, shows the prediction, and shows what the experiment does. And you see for some molecules like this phenol, it's almost spot on, whereas for other molecules like this nitro substituted imidazole, it's not very good. And I think there is a question.
Yeah, short one. Can you clear up the difference between validation and a holdout?
Yes, so I think, so I use this nomenclature that I think is best explained in this scheme. So the training data is the data that's used to train the parameters. The validation data, at least in my nomenclature, and there you might find different one in the literature, is the one that is used to train hyperparameters. And the holdout is the one that just evaluates the optimized model to estimate how accurate is your model. So whereas the training is used all the time throughout the epoch and the validation is checked, also the holdout is only checked at the very end. So that's why it's holdout, because it's literally held out. Yes. Okay. But going back to the final code cell, you can inspect some molecules and you'll see some are really spot on. This phenol is spot on. This boronic acid is spot on. But this molecule is not very good. This molecule has a quite bad error. And this is probably because this is a bit of a strange molecule, because this is the enol of a carboxylic acid. So it's a bit of an interesting molecule. And you see the prediction says it should be 6, but the experiment is 2. So this one, it doesn't predict well at all. Whereas for phenols, it seems to be doing quite well. If you run this code cell again, it will pick another 6 random molecules. Actually, it will pick random molecules from the holdout data and again, print the predictions. So you can then see, well, if you have this interesting molecule here, it predicts it quite well. Whereas if you have a molecule that has both the carboxylic acid and an amide, so basically this is an amino. I think this is glutamine or something, or like glutamine amide, the amino acid. I think so. I'm not sure now. And for this, it actually doesn't predict the pKa so well. So whereas for this molecule here, it does predict it well. So you can see for some it predicts it well, for others not. And And yeah, I mean, these were the basic steps of doing supervised learning. I know we're a bit over time. Sorry for that. If there are any final questions, maybe we can do that, but maybe I don't know if we want to still do the quiz. But yeah, thanks a lot for following.
Yeah, it's late before, I think. The States fairly so, it's 5:15.
Yes. Okay, so for those online,
So we have a recording, I think. The recording will be shared. Is that too much?
Hopefully.
Okay. So you will have an email tomorrow or so, or maybe if we are with link to the recordings, a little questionnaire, and a link to download the certificate if you like. And yeah, everyone download the certificate. The question was just for the fun of it.
yeah.
We'll run something and
Yeah, for those people online, I will just repeat, because we're over time, we will skip the questionnaire, but you will get, let's say, feedback and I guess certificate through email. Thanks a lot for following the course online. And yeah, and also I guess, don't forget there will be more events, satellite events to the ChemAI tomorrow and on Friday, the ChemAI. So don't forget to join there, and thanks a lot. And with that, I will log off.